Okay. Hi, everyone. So thanks for coming today. I see it's mostly Arweavers in the audience. But woo, indeed. Yeah, thank you all for making it. Yeah, I wanted to talk today a little bit about the internet and trust. When we were building AO Core, which is the primitive that basically runs AO, the hyperparallel supercomputer we're building on top of Arweave, we had reason to spend a lot of time thinking about how you could say commerce on the internet, but also more broadly how the relationships of trust in cyberspace actually play out in real life, in the current internet, and how that could model or map onto more trustless systems, and how you'd actually make that work at scale. Because AO already looked quite a lot like the existing internet in architecture. But the blockchain-based consensus models of trustlessness don't really scale to that environment. So with a traditional blockchain, really with almost, I guess the only exception is rollups, but with every other type of blockchain that exists right now, there's this fundamental idea that you have many different validators of the different transactions that happen in the system. And I think you can model each of the transactions that happen as relationships of trust, right? So in the traditional internet, you would have this situation where a user speaks to their bank and they say, hey, please deposit some of my assets into an exchange. And then they would ask the exchange to swap them, and the exchange would then inform the other participants that were counterparties to that transaction about the state transformation of the system, essentially. But what doesn't happen in this model is that many people that were, you could say, tertiary, outside of the transaction itself, were even aware that it occurred. And that makes the internet extremely scalable. And it also makes blockchains, which do the opposite of this, extremely unscalable, generally, by default. So AO already had this sort of fundamental idea of, instead of having one global shared state, we should have many different interacting but independent processes in the system. So that sort of models the situation you have here. You have the users, and they can also be different agents in the system that are autonomous programs, and exchanges and banks. We have like liquidity pools and AMMs and on-chain order books, and also obviously token processes, which essentially fill those roles. And they all already act independently. But I think after spending a lot of time thinking about it, what we realized is that what we're trying to do is basically just add a trustlessness layer to the existing internet, rather than building something entirely new from the ground up. And I think this is inevitably where things will have to go if these technologies get adopted. And the problem itself is sufficiently large, I think, that it is definitely worth addressing. So even with a traditional blockchain-based system, and this is like really underappreciated, everyone thinks when they're interacting with Ethereum, yeah, my transaction is trustless, right? Well, actually, it's not really, because almost all the time, people aren't running their own validators. And when they're not running their own validators, they're having to rely on an RPC service to give them a state representation. And interestingly, that Bybit hack a few days ago, it turns out that actually that appears to have been an attack on the Gnosis safe infrastructure that was serving the web pages, that was specifically targeted. It only activated when the Bybit wallets connected to the front end, and then it swapped out the transactions that they were signing. And so you see this models exactly this situation. So you have Ethereum, this sort of green zone here, where, yes, the interactions are actually trustless. Or, I mean, arguably, if you want to get like philosophical almost about it, you need to trust your own computer. So like, in what sense can anything truly be trustless? There's always trust somewhere in the system, right? Like your machine itself might not be trustworthy. And this becomes slightly more practical when you think about things like TEEs in CPUs, or RD-RAND, the instruction that Intel had that was supposed to generate truly random numbers, or at least pseudo-random but trustworthy numbers. And it turned out that actually the NSA had a backdoor in RD-RAND, so the numbers that they were producing were not, in fact, properly random. They had a backdoor. You even need to trust your own machine. With TEEs, you have to trust that AMD doesn't just sign to say, yeah, trust me, this key is inside a physical piece of hardware that we ship to people. That's a high level of trust. And there's a bunch of others. So yeah, the quest for true trustlessness, I think, is almost futile. There's no way to directly connect with a machine that will remove every single layer of trust. And even then, you have to trust the software. So the question is really about trust minimization rather than trust removal from the system. But when you use Ethereum, for example, so when the Bybit multi-sig participants were logging onto the website, they were trying to move their funds around, what they thought was a trustless system actually turned out not to be, because the edges of the protocol connect to the user via private, but not, would you say, state transformationally secure systems. And the cost of this in the real world is enormous. Like, people don't think about it because as far as I can tell, everyone is so used to having to trust the services that they work with that it's just like subconscious at this point. But I think a really easy way to see it in practice, or to gain some sort of sense of the cost of it in reality, is to look at the cost of storage in different cloud providers. So Amazon will charge you $24 per month per terabyte, which is, I mean, you can take $150 to the nearest Best Buy and you get like a 16 terabyte drive. So for 1 month, you're paying twice as much per terabyte as you're paying for the entire drive lifetime, just for the physical hardware. And yes, there's a lot more that goes into running the physical hardware, but it gives you a sense of the level of margin here. And there's also services like Backblaze, B2, which is actually like pretty well trusted. It's quite widely accepted as legitimate. And their cost is $6 per terabyte month, which is a fourth of the price. And yet, most of the business still goes to AWS. And then there's Arweave, which charges you about 78 cents per terabyte month. That's what the miners pay on a per month basis, or rather are paid on a per month basis. And then there's Chia that pays its miners 12 cents per terabyte month. So the markup from Chia, those miners, to AWS is 200x. It's like enormous. You could, in theory, if you can orchestrate the network correctly, offer storage at 99.5% less than the price that Amazon is willing to sell it to its customers. And those customers are willing to buy it at like en masse. If you could get this right. So the cost of trust is extremely, extremely high. That is really the only thing that Amazon has, that and distribution to existing clients, that Chia doesn't have. Although actually Chia doesn't let you store data, so it's slightly moot point. But if it was like Arweave and it allowed you to add data to it, then this would be the case. And certainly for Arweave even, it's going at like 26th of the price, something like that, relative to AWS. And I don't think it's just hardware provision or sort of compute fundamentals, you could say, like the things that you would otherwise buy from a cloud provider. It extends to everything you do on the internet. So every exchange, for example, they take a small fee. Every ETF, I think, is a really clear example, because the ETF is actually just algorithmic. Like, when someone buys an S&P 500 tracking fund, they don't want anything else to happen other than the obvious basic algorithm, which is just maintain the weights correctly in the fund. That really isn't super difficult. But if you look at the amount of volume that goes through those systems and their fees, you see that actually, collectively, we're paying an enormous, enormous cost of that trust. So it seems like a worthy problem to solve. So AO is already a network with a similar architecture to the internet. It works by having many parallel executing processes with messages passed between them, rather than having a single consensus layer, which will fundamentally never scale. And you can see that it will never scale because you can how many validators multiplied by how many transactions do you want to have in the system, right? So for every interaction that happens in the system, if you were to scale that out to the size of the internet, you would have to have some multiple on top of that of people running validations of it. It works at small scale, maybe like 3 or 4 validations, something like this. But you can't get it to the scale that, say, Ethereum or Bitcoin is trying to right now, which is like 10,000 or 12,000, I think even up to different times, like 60,000 validators of every single interaction. So that's obviously not going to work. And I think the Ethereum community is also moving away from that model towards something that is closer to AO in some senses already. So we have all these parallel processes. And then it's also very clear that the trust that you want for moving $1 billion worth of Bitcoin is definitely not the trust that you need for a microtransaction when you're trying to stream a video on the internet, or really any like small transaction, like $5, $10, just doesn't need the same level of security, and you absolutely have to pay for that security. So like, it seems like a model that's not going to work. So instead what we do is we have a modular and flexible mechanism for adding security. We provide the primitives, and then on top of that, you can pick the security that works best for your use case, and then people can interact. Like, the important part is that you maintain the ability for people to interoperate between the different processes in the system. And we can do that with what we're calling AO Core, which is the primitive underneath AO, the supercomputer that we know and use today. So what we did when designing AO Core was not just to build out that specification I just described, but also then to embed it inside the existing internet infrastructure, such that if we were to gain wide adoption of it, there would be very little change required for the existing systems. So instead of building everything from the ground up and having sort of separate network, if you will, that exists on top of the internet, we embed it into the technologies that already exist. And then that makes adoption of it extremely, extremely simple, and subsequently much more likely to occur, we think. And all of this is based on this new internet standard called HTTP signed messages, RFC 9421, which basically described it's actually kind of interesting. Like, most people think that the internet is already secure, or because they have HTTPS, they have some kind of trusted relationship with the other server. And it's a bit in the weeds, but it's a curious point maybe for a developer audience. Actually, the way that HTTPS works, or TLS, which is the mechanism on which HTTPS is built, is that you use public key, private key pairs to authenticate and initialize a channel between two parties. But then you use symmetric encryption in order to actually pass the data between them. And this creates a problem, which is that the data that you get is non-repudiable. So both of the parties in that TLS channel could claim that the other party said whatever they wanted them to, because they have the symmetric key. There's no ongoing authentication. And so with HTTP signed messages, they were trying to fill that gap, basically, and create a more standardized way of actually doing what OAuth does, letting people authenticate themselves in a single HTTP request and validate with the server and get a trusted response back. And so when you use AO Core today, or actually any computation running inside Hyperbeam, so that includes AO processes, you get back a signed message. And it's not just a signed message on its own. You also get back a hash path, which is, it's like if HTTP paths, those things you put in the URL bar, were blockchains. And you get a reproducible, essentially reference to a position in the compute state space. So for any of the compute that you could perform, or any program that you might want to run, there is always a certain constrained set of different states that that program might be able to get into. Well, this allows you to address each of those in the same way that you address a HTTP resource on a web server. And then that's attached to the signature you get. So the signatures you get back are attestations of both the path that the server claims that it evaluated for you, and then also the content that is found at that path. And the net result of this is that you end up with a network that pushes the boundaries of the trustless space or trust minimized space, depending on which type of security model that you use, right the way to Alice and Bob at the edges. So not just, in fact, actually a good example would be this Bybit hack. Well, if the servers that Safe were using to serve that UI from were part of the system, you would have been able to validate that the data that was served back was not actually legitimate. All right, that's all we got time for, but we have an entire sort of program of events for Arweavers later in the day. I think we start at 3 p.m., so I hope to see you all then. Thank you.